This video is going to be a bit more of a conceptual exercise that has two purposes. The first purpose is that we're going to demonstrate one of the properties of interclass correlation that we've discussed. And the second is to demonstrate how we can use a simulation to demonstrate a statistical property. I found that my statistical analyst game really improved a lot when I discovered that I could use these little simulations to sort of wrap my head around things that I may not have otherwise felt like I fully understood. And there are lots of other really useful things we can do with simulation studies, one of which we will look at in the exercises for this lab. So first, let's just go over the definition of ICC, and we learn that ICC has two interpretations. And the first, for me at least, was a little bit more straightforward, and that's the proportion of total variance accounted for by our cluster structure, or our level 2 variance. So this is a lot like, as we discussed, sort of like an ANOVA, where we're thinking about the proportion of variability attributed to a factor out of the total variability, except in this case, our factor is our cluster structure, where we have lots of different clusters with unique means, and if we know the variability of the cluster means, we can account for some of the total variability in our observations. The second interpretation is that it's also the expected correlation between multiple sets of level 1 observations, and this was the one that I had a little bit of trouble wrapping my head around. Maybe you did too, maybe this is more intuitive for you, but either way, I set up a simulation study to demonstrate what this means and why it's true. So the first thing is that we're going to review the unconditional HLM that we set up in our last video, and this is from the pain data, where we're modeling positive affect based on the cluster means of different people in a daily diary study. And so we're going to imagine that the parameters that we estimated from this model are going to be our population parameters. This is just for the purpose of the simulation. It's just a starting point we can use, but it's somewhat arbitrary. So just to go over it again, our population parameters are in this case, we're going to look at standard deviation terms rather than variance terms, and I'll show you why in a little bit. But we have the cluster means, which have a standard deviation of 1.34. Then we have the residual variance, which has a standard deviation of 1.24. And then we have a population mean or intercept of 5.48. So now let's imagine that, again, these parameters define our population, and that we have 1,000 new participants from this population, and from each of these 1,000 participants, we take 100 repeated observations. And this is, of course, too good to be true in most real-life research settings, but for the purposes of population, you often want to set up situations where you have a sample size that's too good to be true, just so you can really demonstrate what that would look like. So once again, we have gamma 0, which is our population mean, is 5.48. We have sigma mu, which is the standard deviation of our cluster means, is 1.34. And sigma epsilon, which is the standard deviation of our residual, is 1.24. And we know these are standard deviations, once again, because they are not squared. Variances would have the exponent up here. And the reason we want to use standard deviations is because that's the way R likes it. So what I'm going to start by doing is randomly generating 1,000 cluster means. And these are going to match our population parameters. So they're going to have, these cluster means are going to have a mean of 5.48, and they're going to have a standard deviation of 1.34. And to do this, I can use the R norm function. And what this function does is draws a random number from a normal distribution. And there's 3 arguments. The first argument is the number of draws you want to make, and then there's the mean and the standard deviation. So here what I'm doing is I'm calling for 1,000 draws from a distribution with a mean 5.4796. I'm being a little bit overly precise here, just for the sake of this study. And then a standard deviation of 1.3376. So now I have my cluster means. And I need to take these, and I need to then generate 100 observations from each cluster, but I need to add residual error to each observation. And that can be obtained by drawing from another normal distribution, this time with mean 0 and standard deviation equals sigma epsilon. So the first thing I'm going to do is repeat my cluster means each 100 times. So this should give me a variable that just has each of my cluster means repeated 100 times. So it should be a length 100,000, and I just check that here to be sure. So now this is has a length of 100,000, and it should have 100 observations of each value. And I just check that with a frequency table. I only look at 10 of the observations just to keep the screen from getting overly cluttered. And I see that I have 100 observations of each of these values. So everything looks good so far. So now what I need to do is I need to take these cluster means, which are repeated 100 times each, and perturb them with this residual error. So each individual observation now has a little bit more error above and beyond the variability in the cluster means. So I do this by creating a residual, which is 100,000 observations with mean 0 and standard deviation equals sigma epsilon 1.24. And then I take this residual and I add it on to my repeated cluster means, and I check to see what this looks like. And so these should no longer just be repeated cluster values, and they are not. We see that we have lots of different values here. So it looks like our simulation for our first set of data was successful. So now what we have essentially is a simulated set of observations. We have 100,000 observations from 1,000 different clusters in this level 1_1 variable. So now what we're going to do is simulate a second set of data. And the key is that this data is going to come from a population that has the same, or it's going to come from a sample that has the same cluster means, but different values for the residuals. So the actual observations are going to be different, but the cluster means are going to be the same. So I use my same cluster means, but I draw a totally new set of random residual values that match the same residual values I drew before, in that it's 100,000 random draws with mean of 0, 1.2, standard deviation of 1.24. But again, these are new random draws, so they're going to be different values. I check again, and we see these are different values than what we had before. If you look before, you see they're not the same numbers. So we now have two sets of level 1 observations drawn from the same clusters. So they have the same cluster means, but they have different values for the residuals. And this is the key to explaining the second interpretation of interclass correlation. So we have all this variability that's already explained by these cluster means, but the actual daily observations are different. So we essentially have two sets of level 1 observations from the same sample. And now to check our results, we correlate our two sets of observations, and we should expect, based on our second interpretation of interclass correlation, this correlation would be equal to our ICC, so it should be 0.537. We check our correlation, and it's pretty close. Our simulation seems to have given us a correlation that came pretty close to matching our expectation. It's off in the third digit by 0.001. So we've done this once, and a lot of times what you'll do in simulation studies is take a process like this and then repeat it many, many times, and then check the distribution of the results. So here I'm going to repeat this process 1,000 times, and I'm going to do this by using a loop. And to use a loop, I'm going to start by just initializing a totally empty variable with just 1,000 NAs or missing values as placeholders. And then as we go through the loop, each time we repeat this process that we just went through, I'm going to overwrite one of these NAs with a correlation. So let's take a look at how this looks. So first, I create my completely empty variable, so it's just 1,000 NAs. And then I'm going to start my loop, and in this case, it's a for loop. And the way a for loop works is you start with this for term, and you see it's a slightly different color because it's a special command for a loop in R. And then in parentheses, I specify how many times I want to go through my loop. So I here is a variable that indexes each iteration of the loop, and I'm saying I want to go through my loop 1,000 times, to go from 1 to 1,000. And then within the loop, I can index which iteration through the loop I'm in by referencing this I variable. So inside the loop, what I'm telling it I want to do is exactly what I did before. I just want to do it 1,000 times. So I start by generating my cluster means, and then I repeat my cluster means 100 times. Then I add a set of residuals onto these repeated cluster means. I just shortened it here. Instead of saving the residuals as a separate object, I just added them directly on, just to save space on the screen. Then I do it a second time. And so now I have two sets of level 1 observations from the same sample. And then I check the correlation between my two sets of level 1 observations. And I write it to the ith index in my correlations variable. So what this is saying is that the first time I go through the loop, this will be the number 1. And so the first NA will get replaced by the first correlation. Then I start my loop again, and the second time I go through my loop, this will be the number 2, and so the second NA will get replaced with the second correlation. And this will continue 1,000 times until I is the 1,000th or last iteration, and then the last NA will get replaced by the last correlation. So now this correlations 1,000 variable is populated with 1,000 correlations, all drawn from the same process, and I can look at the distribution. So I start just by calling a summary, and we see the mean and the median here both almost perfectly match our expected ICC, but there is a distribution around them. The fact that the mean and the median match tells us that this distribution is pretty symmetrical. And to demonstrate even further, we can plot it with a histogram or a density plot. In this case, I'm doing a histogram. And we see here that this is indeed a nice symmetrical distribution that is peaked between 0.53 and 0.54, which is where our ICC is. And it's got these pretty symmetrical tails. We had one little extra extreme value down here, but even that's not too far off since this is only 0.49 and then 0.57 on the other side. And that's our simulation study.